All right, let's get started. So in the last lecture that was on Monday, we were discussing how to solve or how to optimize a function given there are multiple constraints. And specifically, we started on linear programming, where all the functions that we want to optimize and also the constraints are linear in nature. So there is no non-linearity. And within linear programming, we started with a method called simplex method. So earlier we have also seen graphical method, and followed by the graphical method, we worked out an example using simplex method. So in the simplex method, this is the overview of the simplex method that we discussed in the last class. So let us say this is our problem. Again, going back to the same problem that we have been looking at so far, where we have two crops, crop 1 and crop 2, and we want to optimize the benefits, right? And in the process, we have converted the given data into a set of equations. So where Z is the function that we want to minimize or maximize, which is the net benefit. And this is the first constraint based on the amount of money that we can spend on each crop. And this is the second constraint based on the total amount of land that is available for cropping. And at any given time, both X1 and X2, which are the areas of crop 1 and crop 2, cannot be negative. It should always be more than or equal to 0. So once you have the set of equations or the function that you want to optimize and the constraints that govern the optimization, then you first make sure that there is no inequality. So let us say some of the functions may be less than or equal to, like in this case, we have 3x1 plus x2 less than or equal to 300 and x1 plus x2 less than or equal to 200. So the first step is to remove the inequality, and so you can add a term on the left hand side so that 3x1 plus x2 plus x3 equal to 300, and similarly here x1 plus x2 plus x4 equal to 200. So you're bringing in the equality relationship in the constraints. So once you bring in an equality, then you construct a simplex table where you have basic variables in the first column. Let me find out. So here you have the basic variables. So in our assumed solution, we assume that x1, x2 are zeros, and so we only have x3, x4. And the coefficients of each of these variable from the constraints is written here, along with the right-hand side term of the constraint. So similarly here, we have a second constraint, x1 plus x2 equals to 200. So here we have x1, x2, x4 is 1, 200. Then then once you construct the simplex table, you need to identify which is the entering variable based on the most negative value in the row Z. And then you need to identify the departing variable. So once you identify the entering and departing variables, so the departing variable is when you calculate the ratio RHS divided by the coefficient of x1. The least ratio would tell you which is the departing variable. So in this case, here you see it is 100. So the departing variable will be x3. And then we also have pivot column, which is this column where you have the entering variable. Pivot row is where you have the departing variable, and pivot coefficient is the term that coincides both pivot row and the pivot column. So once you identify all these terms, then we perform the Gauss-Jordan transformation on the table, so that once you perform this transformation, we are trying to eliminate one of either x3 or x4 and bring in x1 or x2 into that place, because our basic variables are x1 and x2, but our assumed solution has x3 and x4. So we need to replace x3 with x1 and x4 with x2. And to do that, we do Gauss-Jordan transformation, where each row of the table is performed some operations, and then you get a new table of new table for the variables. So once you start performing this iteration or transformation, once you achieve all the positive values in the last row for row Z, then that becomes your optimum solution. So if you have all positive values in the row Z, that becomes your optimum solution. And in our case, we saw that the maximum benefit that we can expect was 250 rupees or 250 units. So the maximum benefit was about 250, and the area of crop 1 is 50, area of crop 2 is 150. These are hectares. So this could be units or rupees. So this is the simplex method that we have seen in the last lecture. So now in today's class, we are going to look at one more simplex method. So in today's class, what we are going to look at is called dual simplex method. And this is similar to the simplex method that we saw in the last class. You can tell that from the name itself that it is similar to simplex, but with some little variation in how we approach the solution procedure. So to look at this method, I'm going to write down the same set of equations from the same problem. I know many of you may be bored at looking at the same equations for so long, but please bear with me. So this is our Z function that we want to optimize. So this is called objective function. And we have constraints which are 3x1 plus x2 less than or equal to 300, x1 plus x2 less than or equal to 200. So these are the constraints that we have. Now, we can transform these equations into a set of different equations called dual form. So let us say this is our primal form of the equations. So this primal form of the equations, we are going to convert it into a dual form. And the benefit of doing this conversion from its primal form to dual form is when you have more than two constraints or when you have multiple constraints, then converting the given equations or given functions into a dual form will make it more efficient or make it more simpler to solve the problem, to find the optimal solution for it. So that is the reason why we convert the given primal form of the equations into dual form of it. Now, in this dual form, what we are going to introduce is two new terms or two new variables, y1 and y2. So instead of using x1, x2, x3, x4, in this dual form, we are going to use the variables of form y1 and y2. And here I have written only two variables y1 and y2. And the reason for that is if you look on the left hand side, we have two constraints. So one is this constraint and this is the second constraint. So corresponding to each of these two constraints, we have one variable in the dual form. So if you have one more constraint or one more equation which constrains the objective function, then you need to have one more variable here. So that is the first thing to note, that the number of variables that we are going to use in the dual form are dependent on the number of constraints that we have in the primal form. So these are called dual constraints, dual variables. Now, once we have two dual variables, then we need to transform the objective function into dual form. So if Z is the primal form, I'm going to say Z prime is the dual form. And instead of x1 and x2, we are using y1 and y2. So I have y1 here plus y2, but it is not simply y1 plus y2. There should be some factor in front of y1 and y2. And so if you look at the constraints, the y1 and y2 are related to the number of constraints that we have. So y1 is related to the constraint here, 3x1 plus x2 less than or equal to 300. And y2 is related to x1 plus x2 less than or equal to 200. So the factor for y1 is going to be this from the constraint 1. So it is going to be 300 y1. And the factor for y2 is going to be 200. So our new objective function is z prime equals to 300 y1 plus 200 y2. Now we also need to frame our constraints. So if you look at this constraint, we have 3x1 plus x2. So what I'm going to say is I have 3. Instead of x1, it is going to be y1. Instead of x2, it is going to be y2. Now if I look at the equation below, it is x1, so I write it as y1 plus x2 is replaced by y2. Now what about the right hand side? So on the right hand side, here we have 300, here we have 200. But if you look at, or if you compare the equations on the left and the values that we have carried forward to the right hand side, what is missing on the right hand side is this factor 2. And here there is a 1 that is still not brought onto the right hand side. So these are the two factors or two coefficients that have not been brought into the dual form yet. And so I'm going to bring those two coefficients, which are 2 and 1, and relate them to the two constraints that we have. So this is the transformed form of the given objective function and the constraints in its dual form. And if you look at the sign here, initially it was less than or equal to, and when we write it in the dual form, it becomes greater than or equal to, or vice versa. So if it was more than or equal to 300 here, then it becomes less than or equal to 2. So this is the dual form of a given set of objective functions. And we also have one more constraint, that x1, x2 should be more than or equal to 0 always. And so we would have the same constraint, y1, y2 should be more than or equal to 0. So we have a objective function and a set of constraints that we want to optimize. And instead of doing it in the primal form, we are trying to convert it into dual form. And the advantage of doing that is when you have more number of constraints. Here we have only considered 2, but if it is 3 or 5 or more than 5 constraints, then using the dual solution becomes easier. All right. So this is the dual form that we have considered. So I'm going to write it down again so that we can start the solution process for it. So this is my objective function, which is z prime equals to 300y1 plus 200y2. And we have 3y1 plus y2 more than or equal to 2. Y1 plus y2 more than or equal to 1. And y1, y2 more than or equal to 0. So this is our objective function and the constraints. So now we have to follow the same simplex procedure and try to obtain the optimal solution for this. So I'm going to introduce two more variables, y3, y4, so that we can remove the inequality here. So this equation, I can say 3y1 plus y2 minus y3 equals to 2. And this one would be y1 plus y2 minus y4 equals to 1. So since we have to remove the inequality, I have brought in two variables, y3 and y4. And the above term, I can write it as, or the objective function as minus z prime plus 300 y1 plus 200 y2 equals to 0. So these are the three sets of equations that we have. One is the objective function and the two constraints. Now we have to optimize this using the same simplex table. So if I construct the simplex table, so here we have basic variables, same as before, and we have y1, y2, y3, and y4 RHS. So the basic variables that we start with are y3 and y4. So these would be, one of them would become departing variable in the first step, and then we will bring in either y1 or y2 into its position. Similarly, y4 would become the departing variable next, and we would bring in one more. So here we have to start with the coefficients of y1. It is 3, 1, minus 1, 0, 2. This 1, 1, 0, minus 1, and 1. So this would be z prime, or you could say minus z prime. So this becomes 300, 200, 0, 0, 0. Or we could convert this into minus 3 y1 minus y2 plus y3 equals to minus 2, and this will be minus y1 minus y2 plus y4 equals to minus 1. So our coefficients are going to be negative. So now we have our simplex table, and again we have to identify the entering variable and the departing variable. So to identify the entering variable or the departing variable, so the value with the least or the most negative term on the RHS would become the departing variable. So in this case, it is minus 2. So here y3 would be our departing variable. Since the RHS is least for the row that has y3. Now, once we have a departing variable, we also need to identify the entering variable. And to do that, we have to calculate the ratio. So the ratio is calculated, for example, by 300. So you have 300 here, divided by the absolute value of y3, which is absolute value of minus 3. And then you have 200. The ratio would be 200 divided by the absolute value of minus 1. So now here you have the ratios that you can calculate. So 300 by 3 would give you 100, and 200 by minus 1 or 200 by positive 1 will give you 200. So the ratio now becomes 100 and 200. So the entering variable will be the least of the ratios. In this case, 300 is the least value, which is below y1. So y1 would be our entering variable. So once you identify the entering variable, departing variable, and the column, which is the pivot column and the pivot coefficient. So in this case, the pivot coefficient is minus 3. So this is our entering variable. This is our departing variable. And then we also have the ratios 100 to 100. The element that is common to both pivot row and the pivot column. So this is our pivot row and this is our pivotal column. So the coefficient that is common to both pivot row and pivot column would become our pivot coefficient. And once we have this pivot coefficient, then you apply the same Gauss-Jordan transformation on the simplex table. And once you start applying the Gauss-Jordan transformation, you would arrive at an optimal solution. So in this case, if I iterate it again, so in the first scenario, y3 is replaced by y1 after the first iteration, and the second iteration you would replace y4 with y2 and perform the row operations. And after performing the row operations, what you get is this. So what you observe here is minus z prime equals 250, minus 250, or z prime equals 250. So meaning the optimal solution is, or the maximum solution is z equals to 250. And you have y3 equals to 50 and y4 equals to 150. So these would correspond to the solution of x1 and x2. So you get the same solution. So for x1, previously we saw it was 50, x2 it is 150 hectares, and then the maximum benefit expected is 250 units. So obviously the optimum solution is not going to change whether you follow the simplex method or the dual simplex method. But what is going to change is the number of iterations that you need to create this simplex table, or the number of iterations that you need to do the transformation of the rows is going to be minimal when you have the dual form of the equations. So that is the advantage of converting the given objective function into its dual form and trying to solve it using the simplex method. And when you have more than two constraints also, this is going to be advantageous. So this is an example to demonstrate how the dual simplex method can be applied for irrigation problems. So this covers the syllabus for mid-semester exam, which for you is going to start on 28th, if I'm not wrong. So the syllabus for mid-semester is going to be up to today's lecture. And next week, we are going to start on dynamic programming. So in dynamic programming, we will also see some examples. And because we missed some of the classes in the last 2 weeks, I would like to, during your mid-semester exams and during the mid-semester break, I would like to record some lectures and upload it so that you can watch it later. So that would be mostly on river basin management that I plan to record and upload on Google Classroom. So beyond this, if you have any questions, please feel free to ask. So since we have covered the syllabus for mid-semester, I'm going to send out a link for feedback so that I can understand your response to the course so far and what changes you would like to make as we move forward. So please provide your feedback once I send you the link. So do we have any questions? As usual, the recording is going to be available for you as well.